The first speaker of the morning session is Pierre Del Moral. He's going to talk to us about some theoretical aspects of ensemble Kalman filters and particle filters.
Okay, thanks, Dan, and thanks for the invitation. I will try to make an introduction not too long. So I started working in this area in ensemble Kalman when I came back from Australia. I used to work only on particle fluorescence like that. I need to find, let's say, another type of subject. Then I started reading this article by Leglin, Mombe, and they called large sample asymptotic for the end in 2009. But all the rates they succeed to have something with the time. So if you have exponential of time, of course, after some time, after 5 or 6 iterations, you need more particles than you can see in the universe to get some precision. So then it's not large sample asymptotic, maybe super large. And then I discussed with people working in this area. They say if the dimension is 1 million, we take 20 particles. They say that's something I don't understand. So I tried to answer. It's more or less applied to nonlinear models, for example, the Lorentz model. But the Lorentz model turns around like that. It cannot explode. So if you create an algorithm that explodes, trying to follow the Lorentz model, something wrong is happening. Because if you just do prediction, nothing wrong may happen. So complicated. So I say, okay, let's start again, everything from scratch. And yes, to say something also on this article, as usual in probability, when things get too complicated in discrete time, you enter in continuous time. So I try to see how the analysis translates in continuous time. But the problem is that the bounds here explode when the time step tends to infinity. So that's very bad also. So in fact, you need to restart everything from scratch. So that's what I'm going to present you today. Then I started working in this in 2016 with Julien Tugot. And then after that, I came back to Australia for part-time and I discussed a lot on that with Adrian Bishop. And we did some work on this area, mainly for linear Gaussian models. So today it will be relaxed for you because it's only Kalman filter. So maybe for those who don't know Kalman filter and do only nonlinear filtering, I'm sorry for that. But it's not so simple, the Kalman filter. For example, the stability of the Kalman filter, there is a huge theory started by Kalman and BC in the 60s. Some parts of it are wrong. So it's complicated to use this result based on wrong arguments. But at the end of the day, De Leon, I think, corrects a lot of things. So everything is corrected more or less in this area. So you can use the stability of Kalman filter to try to say something on the long-time behavior of this type of model. So let's start this presentation. So I will discuss first on continuous time, then I will give you some performance analysis, discuss nonlinear filtering, but only extended Kalman. So it cannot be seen as an optimal filter. It's more an observer in the terminology of signal processing. Give you some link between discrete time ensemble Kalman and particle filter, and we'll finish. So let's start with the continuous time filtering problem. So everything is very simple. You start with a linear Gaussian model, X. You observe the signal with some matrix C, so maybe some coordinate of the model. And you put some noise, and I call Y the observation up to time t. So of course, you need to have some observability, controllability condition, because if you observe only the first and here, the other ones are not correlated, you cannot see the second one. So if the second one is exploding, then everything explodes. So there are plenty of controllability, observability condition. I will not so enter into that. So the optimal filter, if you start Gaussian, if you start initially from a Gaussian variable, everything remains Gaussian, and you simply need to compute the conditional mean and the conditional variance. So just have a look here. The conditional variance really tells you that your estimate is close to the true signal, and PT represents the quality of that. Okay, so if you take the trace, you have the variance. So that means that the behavior of the covariance matrix tells you how the quality of the estimate. Okay, so that's quite important. If you are in nonlinear setting, that's not true. But for linear model, it is true. So the covariance capture the stability of the estimate. So the Kalman filter is the evolution of the conditional mean. So that's called the innovation process. This is orthogonal to the constant, the mean is 0. This is called the gain. And you see that the gain is connected to these matrices and the covariance matrix. So you need to compute the covariance matrix to run the Kalman filter. And it's nice to see that the covariance matrices satisfy a deterministic equation which can be solved offline. So if you can solve offline this equation, so S is used everywhere in the talk. So it's this crazy matrix, C prime sigma minus 1C. So if you can solve this equation offline, you plug it here and you solve the Kalman filter. Or the steady state is to compute the fixed point of this equation. You just say when P infinity is when this is equal to 0. You plug it here, is no more the Kalman filter, but it's called the steady state Kalman filter. So there are many ways to compute these quantities, but in high dimensional space, it's a bit tricky. And if you discretize in time, this doesn't work because you can fall outside positive matrices. So it's a bit tricky. You'll have to come back to the discrete version of the Kalman filter. Okay. So so I start from something very simple like that, and I'm going to make it complicated. Okay, so you start for linear Gaussian, everything is Gaussian, simply the mean and covariance, and now I'm making things complicated. For example, if I talk about a Gaussian random variable, I want to represent the Gaussian random variable by a random variable. The Gaussian, I don't want to say I have a Gaussian, I just want to represent a random variable whose conditional mean is equal to that and whose conditional covariance is equal to that. Okay, that's the trick. I want the stochastic version of the Kalman filter. I want to write a process whose conditional mean and whose conditional covariance coincide with the one of the Kalman filter. Okay, so that's the trick. So we are looking for something which may be nonlinear, such that, so this is a diffusion, let's say, such that if you fix the observation, then you obtain the law of the diffusion coincide with the Gaussian, with the Desired mean and the Desired covariance. Okay, so that's the thing. I don't want to, given the observation, the conditional mean and the covariance are deterministic if I give you the observation. So now it's a bit more tricky. I want to design a nonlinear process, so the extra diffusion everywhere, such that if I stop the process at a given time, the law of this process is a Gaussian. So that's the trick. And the process is allowed to interact with the conditional mean, which is, so E of x is the vector of x, the coordinate of x. So that's a column vector, that's a row vector, so that's a matrix. So this P eta t is the covariance of the law of the process. So the process is possibly interacting with the covariance of the law of itself. So that's complicated because for people working in Makin-Vlasov equations or diffusions, every coefficient typically are Lipschitz, and this is not a Lipschitz function. It's quadratic. So that you cannot apply all of these tricks. Okay, so I give you plenty of examples. There are many processes such that this is true. So the first one is called, for some reason, the vanilla ensemble Kalman filter. It was introduced by Evanson with some mistake because he didn't consider that, but if you just add this, is correct. So you see that this is a diffusion. So it's a kind of, it's not an Ornstein-Lembeck because A can be unstable. So this is a linear diffusion. You have a kind of innovation, extra noise, and this is the covariance of the state before. Okay. Understandable by everyone? Fine. Second one is more simple. Instead of adding extra noise here, you take the process, you add the mean, and you divide by 2. Don't know why, but it's like that. I have not invented that. So that's the discrete time Sakov and Ock in 2008. Again, the diffusion here interact with the covariance of the state before. And some question, if you make the discrete time approximation, you are not consistent with the discrete time Kalman. Okay, so everything is in continuous time, it's just for mathematical reasons. Okay, and the third one is the pure transport equation. I think was introduced in discrete time by Reich and Cotter 2013. It's simply, you see, you have extra noise here, extra noise, extra noise, extra noise, no noise. And this one has no noise and nowhere. So there are no noise in the prediction, no noise in the observation term. So the randomness only comes from the starting point. And that you can check is correct, that the law of the process, if you start from Gaussian, the law of the process in this pure transport model, it's again Gaussian with the Desirel mean well covered. Trick. I don't know how they found this. And you see this process as a kind of repulsion or attraction around the mean. And there are many other, and infinitely many other. You can add this time of term here with the skew matrix, and it's correct. So plenty of choices. Okay, so again, in everything I wrote, it's tempting to replace the linear stuff by and the sensor function by a nonlinear function like that. It's often done in practice, but of course, if you do that, you are not consistent with the optimal filter. Okay, everything I've said is correct for linear Gaussian models. If it's nonlinear and you do this trick, you can do the trick. You are creating an algorithm, fine, but it's not optimal at all. The algorithm you have decided to design something. It's clear for everyone? Okay. So the ensemble Kalman is doing these things. So you see, if I want, for example, to sample, let's say this diffusion, you sample the noises here. You put to the same observation to everyone. You sample noise, so you can sample IID copies of that by sampling plenty of noises. And as soon as you need the covariance matrix, you replace the covariance by the sample covariance. That's it. Okay, so that's quite simple. You replace, so I sample IID copies of the noise everywhere, but I have just replaced the true covariance of the random state by the sample covariance. Very simple to define. And M is the sample mean. So you can do this for all the classes I have discussed. Of course, in doing so, you make things complicated because you start from Kalman-Bussy filter, everything is linear Gaussian. Then you introduce a nonlinear model, fine. And then you end up with interacting particles. And the particles are interacting, each one is interacting with the sample mean. So it's a mess to analyze. So you start from simple and make it complicated. So that's the way people do in ensemble Kalman. So we try to understand how it works, why this works, at least when n is quite large. So the first question, if when you look at this, I'm not solving any type of Riccati equation. I'm just using the sample covariance at each time. I really don't care about the Riccati equation. I sample plenty of IID, not IID. Say, I sample plenty of IID copies of the noise, evolve the particle, and they are their own sample covariance. But the Riccati, I don't need to compute the Riccati here. Okay, so that's the main difference. So let's look at the evolution of the sample mean. So the sample mean evolution, if they approach the one of the Kalman filter, there should be some reason for that. So that's one trick, is to write the evolution of the sample mean as the Kalman filter. So if this was 0, this will be exactly the Kalman filter equation. Okay, but instead of PT, you have the sample covariance. And here you have some extra term, because for example, here, when you sum IID copies of Brownian motion, they go to 0. It's the martingale and they go to 0. So it's normal to have a martingale perturbation here. And when the number of samples tends to infinity, this perturbation disappears. Okay, so that's the idea. So this type of equation looks nice, but it's a bit tricky to analyze for plenty of reasons. First, this is a Coulomb vector of martingales. So you have plenty of martingales. That's the sample mean. So Coulomb vector, plenty of martingales everywhere. If you take 2 martingales, the product is not a martingale. So you need to understand what is the angle bracket. So what to subtract to have again a martingale. So it happens that if you take, so that's simply a notation, but you can think in dimension 1. So that's the angle bracket of the martingale here. But if you have plenty of martingale, that's you take two of them, you multiply the two, and the angle bracket between these two is given by this expression, let's say. Okay, so let's think in one dimension. So this U and V are important. What is U and V? So in case one, remember you have noise in the prediction, noise in the observation. In that case, the U and V are not null. They are given by R and S. In the second case, you didn't have noise in the observation. We took the process at the mean divided by 2. So in that case, the noise, the V here disappear. So it's quite nice to have the mean disappear in the angle bracket, because the angle bracket represents the square, the mean of the square of the martingale. So if the mean of the square is increasing, that's very bad news. Okay, so this is better. The deterministic ensemble Kalman is better than this one in a sense. And in the third case scenario, as I said, the noise comes only from the beginning, so there are no more noise, and you are solving the equations without any perturbation. So that's 0, 0, and 0. The third case is pure transport. So the sample mean satisfies the same equation as the Kalman filter, except it starts from the sample mean. Okay, so if you understand the stability of the Kalman filter, it's done. Yeah. Also, now look at the sample covariances. The sample covariances, the little p, I'm using little p because capital P is used in the terminology of a Kalman filter as the covariance matrix and the Riccati equation. So for me, little p is the sample covariance. Okay. So the sample covariance satisfies the same equation as the Riccati equation. So that's good news. But you have an extra martingale here, and the martingale is even more complicated than the other one, because this is a sample covariance matrix. So it's a matrix, and that's a matrix of martingales. So you have martingales everywhere. So it's not so easy to handle. But if you take two of them and you make the product, there is a way to compute the angle bracket. So the angle bracket is given by this expression. Of course, in multi-dimension is a bit complicated to write, but let's say in dimension 1. So you have something which is quadratic if V, third cubic, if V is not 0. So that's very bad news again. Okay, so V positive, you are cubic. So if you do discrete time, that will be something may explode because you don't have Lipschitz properties and all of this stuff. But everyone knows in statistics that if you have IID copies of Gaussian, and you take the sample mean and the sample covariance, these two guys are independent. But here is not the case because they are interacting everywhere. But the perturbation of this guy and the perturbation of the sample mean are orthogonal. So that's quite new. Nice. Okay, so if you want to see in dimension 1 what's going on and the link with existing literature, I rewrite the Riccati equation of the sample mean. So here is the sample variance. So the sample variance has the same law as the evolution of this equation. So you see, you recover the Riccati equation here. That's, so that's the martingale term. So you can represent the martingale is continuous trajectory. So you can represent it with Brownian motions. So here, this is a matrix of plenty of Brownian motion. You take the square root of the sample covariance and the square root of this term. And that's a way to represent in terms of random matrices and Brownian motion, the evolution of this quantity. Okay, in law is the same. So you can see it's not so simple to analyze, except in some situation. For example, if S is 0, in fact, you are not doing filtering. It's simply the Hochstein-Uhlenbeck copies. So you have the sample covariance of Hochstein-Uhlenbeck IID copies. So this is known as the Wishart process. For the Wishart process, you have a lot of things. You can compute the law at any time t. So now something even more simpler, you take all the matrices here diagonal. All of them are diagonal. And I take the second case scenario, the deterministic, the Sakov-Henok stuff. So V is 0 to simplify this term. So it's even simpler. And what happens? You end up with the eigenvalues of non-colliding, the eigenvalue of the sample covariance matrix satisfy what is called the Dyson equation. So and this equation arise in this type of equation arise in physics, and they are not so simple to analyze. So at the end of the day, you say, okay, I'm entering into a subject which is getting very, very complicated. Okay, so that's to make some link with existing literature. So now let's see how we have analyzed this type of model. In fact, it's always the same trick. Since 30 years, I'm using the same trick. You see the approximation as the true plus a perturbation. So if you control the unperturbed model, then the perturbed model should be under control. So that's the main idea, typically. So that's the idea. If you, for example, if you have IID copies of some random variable and you look at the sample mean, there is a way to rewrite the sample mean in terms of the mean plus a perturbation. So this perturbation is very simple to define because it's the mean, the sample mean, minus the true mean multiplied by square root of n. So everyone knows that if you do this operation, you converge with the Gaussian with the desired variance. Quite simple. But the way of writing like that shows that this is the unperturbed model, and that's the perturbation. So in doing so, you know that the perturbation as a martingale type is in the average is 0. So in the average, you don't perturb the things. And the variance that correspond to the angle bracket if you had a martingale, you have the variance of the random variable because here you are dealing with IID copies of the random variables. Okay, so now it's quite simple to see that if this process is stable, you can get uniform in time estimate. And if this process is unstable, then it will explode. That's quite simple to see. You look at its equality everywhere, so there is no way to bypass this. You need the unperturbed model to be stable. If it's unstable, you can do that, but you will get a very crazy bound. And in fact, here is equivalent. Okay, so in fact, when you look at this, you see, and we have seen the previous perturbed model, we need to study the stability of the Kalman filter. That's it. And if we understand correctly the stability of the Kalman filter, we are done, roughly. Okay, so that's some strategy. So something in one dimension, in one dimension, you can solve the Riccati equation directly. So that's quite easy because the unperturbed model can be solved explicitly. In that case, you have two fixed points. One is negative, one is positive. And you converge, so that's the flow of the Riccati equation starting at Q. You converge to the positive fixed point exponentially fast. And this exponential fast constant, you can see that even if A is unstable, if A is negative, for example, minus 1 million, it's even better for you. You converge faster to the fixed point. So that's the quality of the Kalman filter, is that even if the signal is unstable, this guy, the Riccati equation, is stable. That's important. And this is because you can solve the Riccati equation. So thanks to that, you can look at the Riccati equation in one dimension. So that's the one dimension sample variance. It's equal to that with the Brownian motion. If you have enough particle, the origin is repellent. But there is a problem. In the first case scenario, which is called the vanilla, if you look at this diffusion in one dimension, it has an invariant measure. But the invariant measure has heavy tails. So if you have heavy tails and you try to control some moments, it may not work. You need more particles to control higher moments. So that explains why in the analysis, you need to say, if I have enough particles, then I can control that. Because you cannot bypass of that because of the heavy tail. In the second case, the Sakov-Henoch model, you have Gaussian, so V is 0 and U is positive, you have Gaussian type tails. So that's nice. That means that all the moments exist. So of course, you need to enter into that. So if you want to have a more detailed view of this, you have the convergence of this to the equilibrium and so on and so on. I put some references, you just click on that and they will open. Okay, but to understand why things work or doesn't work, when you compare the Kalman filter to the true signal, you obtain this equation. So that's because this comes because of the observation process. The observation is the signal plus noise. So when you replace the observation, you obtain this type of equation. So you see a recursive equation. So this term is extremely important. This term is the one that will stabilize this noise and will stabilize the noise of the observation. If this term doesn't stabilize the signal noise and this one, then this will explode. And it's not exploding Because when you take the square and you take the mean is the Riccati equation. So it cannot explode. There are a lot of studies on that under consistency and observability conditions. So under some conditions, observability and controllability, there exists a fixed point of the Riccati equation. And this fixed point of the Riccati equation tell you that this matrix, if you take on the fixed point, it's stable or rich or whatever you want to call it. So that's the key part of the stability of Kalman stability theory. That's extremely important. So of course, if you start with a steady state Kalman, you will have instantly the fixed point and this will be stable. So that's why everything is stable, not only the second moment, but all of them. Okay, so that's important. So it's stable even if the matrix A is unstable. So with Adrien, we did some stuff on this type of model because we found a lot of problems in the literature and we tried to fix them. So maybe we made some errors, I don't know. Because it's complicated. For example, if you have two positive matrices, your product is no more positive. So in fact, this is not so simple to understand. It looks simple, but it's not so simple. Okay? But intuitively, this guy, the fixed point, is able to stabilize the unstable diagonals of the matrix A. That's important. But you need S to be strictly, in a sense, positive and so on. Okay. So I have 15 minutes, so maybe I will not enter into that. So something we did is to analyze when you are, so you see this is a matrix that depends on time. When you have a linear system with a matrix that depends on time, everything may happen. It's time varying linear systems. Time varying linear systems are not so easy to handle. Okay, so there is all the theory of Kalman and Bussy to analyze the stability of this guy. You cannot write the integral, the exponential of the integral of the matrices. That's not true. It's the fundamental matrix. You can write the semigroup, but it's not the exponential of the integral of this matrix. Absolutely not. The matrix in time doesn't commute, so it's not true. It's true only for time homogeneous model. So it's really tricky to analyze the fundamental solution of these time varying linear models. So that's already one difficulty. Okay, so I will not discuss on that. So that is something we did, blah, blah. So now if you look at the ensemble Kalman, it's exactly the same type of equation as expected. But because here you are dealing with the sample mean, you have the same type of equation. So you need this guy to stabilize the noise, and the perturbation arriving in the system. So that's the trick. But this, in fact, is not the Riccati equation, it's the sample covariance. So now you imagine you have a linear model. It's time varying, but it's also random. So that's a massive mess to analyze. Okay, so that's the trick. So it's time varying, stochastic type linear diffusion. And so it's very complicated to analyze the stability of these guys. So that's why we made some conditions, sometimes drastic conditions. So the matrix, for example, if the sample covariance explores some space, so this may happen to be ill-conditional, so it can be positive. So it may have explosions. So this explains, I would say, in some sense, that if you run this type of models on a nonlinear system, even the Lorentz or something, even if the model is running in a compact space, let's say, using this, you may unstabilize the system. Okay, you may explore bad places. Anyway, and it is always unbiased. So this property is very simple to prove. But so if you have enough particles, because you are summing rank 1 matrices, so you need to have a lot of rank 1 matrices to get to strictly positive. So you need at least the number of samples equal to the dimension of the problem to get this condition. And it's always under bias. So when it's under bias, that's not a good news because you need this in a sense to be large enough to stabilize. So if it's under bias, that's bad news. So when I discuss with some colleagues in Sydney Uni, they say it's under bias. It was a surprise. In fact, the proof is very simple. It's a surprise, and they say, yes, but it works. So yes, it works for some reason, but it's still under bias. Anyway, so when A is stable, that's the first thing we did with Adrien in 2016, is to say that if you have enough particles, for any power here, if you have enough particles, remember, you may have heavy tails. So that explains why you may need these type of things. Then you can get uniform estimate between the sample covariance and the true Riccati equation, the same for the sample mean. So that was already something important. So we were very happy with that. And when I discussed with Adrian, instantly he told me, but that's trivial, because if the system is stable, you let it goes to zero. And of course, you get uniform in time estimates. Of course, it's not so trivial because I want the square root of n here. But if the system is stable, everyone goes to zero, should be not so complicated to analyze. So that's what, thanks to this critique, we enter into the nonlinear, the non-unstable world. So the unstable world, we did a lot of things. I just don't want to enter into all of them. So if you're interested, I put some references. The very last one I think we did with Dan, it was to estimate log likelihood and the normalizing constant. Anyway, if you are interested, I give you some references. That's it. I continue, otherwise I will be stuck. So for nonlinear filtering, the only thing I understand is the extended Kalman filter. So you take the extended Kalman filter equation in continuous time. Is a bit more tricky because you are linearizing around the system, around the estimate. So you take the drift of the estimate. The Riccati is no more offline computable because it depends on the derivative. So that's called the extended Kalman filter. You do exactly the same trick I did before. So you try to find some diffusion such that the law of the diffusion coincide with the distribution with the mean and covariance coinciding with this. Okay. That's not impossible for the extended Kalman filter because it's you see here it's a recursive equation. So that's quite simple to write. So that's one way to write. When you do exactly as previously, you add noise here, you add noise here, and you take a complicated drift from we do more or less the same as here, but there is an attraction or repulsion around the mean term here. So that's, and you do the same. So if you're interested, I put some references here to enter into this. So that's the only non-linear thing I can do, which has nothing to do with the optimal filter, extended Kalman. So you do exactly the same trick. You replace, you take you replace the true mean by the sample mean. You replace the covariance by the sample covariance, and you continue and continue doing the same operation all the time. So as soon as you know the trick, it's quite simple to repeat the argument and see what will. So now I give you some examples where the drift is, for example, a Langevin diffusion, very stable Langevin diffusion. That's some examples. You can take a potential of that form, So I try to sell this nonlinear model to some journal or to some people. So I need to find example of nonlinear model that fits my conditions. Okay, so that's why I consider some, for example, A to be a gradient, convex. So the signal is nonlinear, but is mega stable. Okay. So the extended Kalman filter is quite complicated to analyze, but it was at least some conditions. So under these strong conditions, under super strong conditions, which are written here, it's not interesting to enter into them. Let's say the signal is nonlinear but super stable. So in that case, you can obtain the stability of the extended Kalman filter, which is not. So that's the stability in 2 Wasserstein norm of the extended Kalman filter alone, without perturbation. And if you use particle, you do a perturbation. So now it's somewhat tricky. So you have now a sample mean and a sample covariance. That's the true conditional mean and covariance of the extended Kalman filter. And you want to have this type of propagation style of curve to compare this and this and to compare this and this. So you succeed to have uniform estimate in time with some very bad constant here. And if the initial starting point is not too large and very large. So you can see it's already restricted, a lot of restriction. There may be a lot of things to do in this area. We have stopped working on that. So just to say that the conditions are very drastic, very stable conditions. And I cannot start too far and I need to have a lot of particles. not a good news, but it may be good news if someone wants to enter into the subject. So is it a happy end story for the ensemble Kalman? No, of course, because we are not dealing with nonlinear model exactly. In practice, it's discrete time. So that's another subject, which is, I think, harder to analyze. So in discrete time, can we have, again, uniform estimate? That's the natural questions. Because there are some situations where some dimensions are very unstable. Can we do some stability theory in discrete time? And for particle filter, you can call it as you want, don't care. But since 30 years, there were a lot of work in this area. This mainly for stable signals, except the very nice work of Nick to understand the stability of the nonlinear filtering equation. If you want to have no trouble, you take, for example, a diffusion reflecting on the compact space, reflecting on the boundaries, and everything goes well. So the conditions are not so crazy, but still, so it doesn't apply for linear Gaussian model, and still nowadays the particle filter are not be proven for linear Gaussian model in dimension 1 uniform in time. So it's an open question since a lot of years. So, okay, so that's it. The second part now, the last 10 minutes, I will try to do quickly on that. So I write the discrete time linear Gaussian model in one dimension. It's written like with matrix-like notation to make you think I know how to handle the multivariate case, which is not totally the case. But in one dimension, it's like that. Everyone knows that the predictor is Gaussian. The optimal filter is again Gaussian. If you start Gaussian again, I'm using this notation and without the at for the predictor. And the Kalman filter say when you have predict, you update, correct, predict, correct. Everyone knows these equations. And the P and the difference are stable for any A. So that's the Kalman theory, or maybe more the Kalman theory, because it's written in discrete time. Okay, so we know all of this on Kalman filter is done. You don't need to touch this type of things. So now let's look at the particle filter as we discussed in discrete time. When you do the selection and the mutation, or you can, okay, the updating or everything you want, the likelihood for linear Gaussian model, the fitness function is the observation. You compare your prediction to the true observation. So that's the vanilla or the bootstrap, or as you want to call it. And the prediction is as soon as you have selected, then you add some noise to see the next variable. So now you try to estimate the sample, the true Kalman filter true mean by the sample mean of this. Okay, but the problem is that with discussion we had when I was in Bristol, I think 2 years ago or something like that, we start thinking on that. And in fact, it happens that if you start the particle too far from the origin, and for example, the scene may start negative, then the L1 distance between the sample mean and the true conditional mean is plus infinity. So that's not numerical analysis. That's let's say a theorem that says that it doesn't work. That's it. Okay, so that's bad news. But the Kalman filter, the ensemble Kalman filter, can do it. So that there is a problem then. So wait. Of course, this may not be the best way to do the selection. Maybe it's not the best way to do the exploration. But if you apply it like that, because these are tuning parameters, it doesn't work. Okay, so the Kalman filter is written like that in discrete time. So in discrete time, you see it's a bit more messy because the prediction of the Kalman it's quite simple, but the correction or the regression formula has a gain that depends on the predicted covariance. That's the evolution of the corrected covariance, and that's the evolution of the predicted covariance. So it's already more complicated than writing the Riccati equation in one line. Okay, but in dimension 1, if you replace this by this quantity, you end up with the discrete difference Riccati equation, and you can solve it explicitly. So now it's good news because you can try to, now you understand perfectly the Kalman filter in dimension 1, you can solve perfectly everything, and you try to prove that the ensemble Kalman in one dimension works correctly. So if you do the nonlinear version, which is the stochastic version, how to define a Markov chain, driven by the observation, driven by extra noises, such that the gain depends on the covariance of the state before. So that's the way to write the stochastic version of the Kalman filter. I'm just adding extra noise here and extra noise here, so that everything is linear Gaussian with the desired mean and the desired covariance. So if you do that, that's what I'm saying. You are consistent. Every time step has the true conditional mean and conditional variance. And okay, what I have written, I cannot see what I have written. So I say, yeah, okay. So when you do there are plenty of in the literature. There are plenty of things here. You can erase this. You can do what is called a square root filter in this operation. If you do the square root filter, in fact, you will not have error in this part. It's a pure transform. You don't need to define a new random variable. Simply the previous one transformed by some deterministic function. So you don't need to make more effort. So you will not be perturbed here. So if you do, you can do simpler things with deterministic updating like square root, adjustment, or transforms. If you do that, which is connected to the unbiased ensemble Kalman filter, the only error comes from the beginning. Because when you look at the evolution of the system, it satisfies the same equation as the Kalman filter, except that you start from the sample mean and the sample covariance. So if you understand the stability of this guy, it's done. Okay, so what you do is exactly the same. You sample IID copies of the chain, and as soon as you need the covariance matrix or the variance matrix function, you replace the variance by the sample predicted variance. So that's the discrete time Markov chain, where you replace here the variance by the sample variance, and here the sample mean. It's always the same trick. Quite simple to see. So when you do these things, you end up with the same equation as the Kalman filter, which has two things. First is the updating, then that's the prediction. So it's exactly in blue, you recover the Kalman filter equation, but you have some perturbation. The problem here is that the local perturbation arriving here are central, so that's fine, but they are related to squares of Gaussians. And having square of Gaussians, if you had diffusion, it was dw square is dt, but here dw square is not dt in discrete time. So you still need to work with chi-square random variable. So it's not so simple. So that's the trick, but you can prove that if you just look at the Riccati equation in discrete time, you solve the same equation that you can solve explicitly up to some perturbation. So if you can control this perturbation, we know how to solve the unperturbed model explicitly, so it's not so complicated to analyze. So that's the trick always using. Okay, so this is an estimate we obtain which is true for any A. So for any A, you can control the bias uniformly in time, and you can obtain also estimate of the bias of the sample mean uniformly in time. So that's good news, and that's true for any A. You have also the LP bounds or the LK bounds, because P was already from here, uniformly in time. We are only in one dimension, so it's very simple, and I can solve the Riccati equation explicitly. So you can derive a lot of result in this field. So that's the paper I did with Emma Orton. So the one dimension is the paper I did with Emma Orton, and that's a work. We try to do the multivariate case. It's a working paper we had since 1 year. It's a bit complicated to finish because it's connected to non-central Wishart distribution. What I need is to have an estimate of inverse moment of non-central Wishart distribution. So Gérard Letac and Massam did some work on this area, but I don't have enough precision to use their result in this field. Okay, I'm done. Thank you.
Questions or comments?